Welcome everyone. In this walkthrough, we'll look at an exam question involving electrode potentials. It's taken from an A-level Chemistry Year 2 past paper. Details are in the description. I'll start with an explanation of how electrode potentials are measured using the standard hydrogen electrode. The question requires students to interpret standard electrode potentials in order to identify a suitable reducing agent. Let's get started. We can think of standard electrode potentials as a measurement of the reducing power of a chemical species. The basis of an electrochemical cell is a redox reaction. The standard hydrogen electrode is used as a reference electrode. It has an E standard value of 0.00 volts. Standard electrode potentials are measured by connecting a half cell to the standard hydrogen electrode. Standard conditions must be used, that is a temperature of 298 Kelvin. Any solutions present must have a concentration of 1.00 moles per decimeter cubed. Any gases must be at a pressure of 100 kilopascals. I'm going to give a brief overview of how electrode potentials are measured using just one example. This will provide enough of the theory required to address the question later in the video. I plan to make another video going into more detail about how electrode potentials are measured in the future. The diagram shows a standard hydrogen electrode. Hydrogen gas is pumped into the system at a pressure of 100 kilopascals. Some older sources might state a pressure of 1 atmosphere. Although 1 atmosphere is very close to 100 kilopascals, this is incorrect and you must quote the correct pressure, that is 100 kilopascals, in exams when required. A 1.00 mole per decimeter cube solution of H+ ions is present in the beaker. Solid platinum provides a surface for electron transfer to take place. Platinum is relatively unreactive and a good conductor of electricity. The temperature must be 298 Kelvin. The half equation for the reduction of H+ ions is given to the right of the diagram. Sometimes these reduction half equations are written with the equilibrium symbol rather than an arrow. It is important to note that this half equation could proceed in either direction, depending on the other half cell that it is connected to. Hydrogen molecules could be oxidized or H+ ions could be reduced. The diagram shows the Fe2 plus Fe3 plus half cell that I will use for an example. Both solutions must have a concentration of 1.00 moles per decimeter cubed. Once again, solid platinum provides a surface for electron transfer to take place. The temperature must be 25 degrees Celsius. The reduction half equation is given to the left of this diagram. This diagram shows the standard hydrogen electrode connected to the Fe2 plus Fe3 plus electrode. A high resistance voltmeter is used to measure the potential difference given in volts. This is shown at the top of the diagram, the capital V in a circle. A salt bridge is used to connect the two half cells. This contains inert mobile ions that won't interfere with the reaction. The salt bridge completes the circuit. Take a look at the table. It is not possible for both of these half equations to proceed in the forward direction. The basis of an electrochemical cell is a redox reaction. Both oxidation and reduction must take place. By definition, the standard hydrogen electrode has an E standard value of 0.00 volts. When these two half cells are connected, a potential difference of plus 0.77 volts is observed. The actual half equations that occur are given here, showing that Fe3 plus ions are reduced and hydrogen molecules, H2, are oxidized. It is possible to use standard electrode potentials to predict the reaction that will occur when two half cells are connected and the potential difference that will be observed. I'll explain how to do this in a future video. Now let's look at the question. Use the data from the table to identify the species that can be used to reduce VO2 plus ions to VO2 plus ions in aqueous solution and no further. Explain your answer. The difference between VO subscript 2 superscript plus and VO superscript 2 plus might be confusing. It will be necessary to look at the formulas on the screen carefully during this explanation. I've numbered these half equations 1 to 5 and will refer to these numbers during the explanation. When two half equations are combined, the system with the most positive E standard value will proceed in the forward direction. Let's look at half equations 1 and 3. E standard of half equation 3 is more positive than E standard of half equation 1. Cl2 will be reduced to form Cl- ions. VO2 plus will not be reduced. Next, let's look at half equations 1 and 4. E standard of half equation 1 is more positive than E standard of half equation 4. VO2 plus will be reduced to form VO2 plus. Fe2 plus will be oxidized to form Fe3 plus. Now, let's consider half equations 2 and 4. E standard of half equation 4 is more positive than E standard of half equation 2. VO2 plus will be reduced no further. Let's address the question. The species to use is Fe2 plus. E standard of half equation 1 is more positive than E standard of half equation 4. Also, E standard of half equation 4 is more positive than E standard of half equation 2. Although the question is now complete, let's look at what would happen if half equation 5 is used. E standard of half equation 1 is more positive than E standard of half equation 5. VO2 plus ions will be formed initially. However, E standard of half equation 2 is also more positive than E standard of half equation 5. VO2 plus ions will be further reduced to V3 plus ions. Thanks for watching. I hope you found the video useful. Please post in the comments if you have any questions or suggestions. Take care and good luck with your studies.